Hello everyone and welcome to another video. So today I want to have a quick discussion on eigenvalues and modes of a linear system. So what do I mean by a linear system? So again, just to refresh your memory, I'm going to assume that we have this nice form of a set of ordinary differential equations of x dot is equal to ax plus b u of t, right? So the idea with this system is that, again, it models a system which has inputs u of t, and in this case, let's assume that the outputs of this system are the entire state vector x of t, okay? So this is basically the linear system in question. So what I'd like to look at today is how do the eigenvalues of the A matrix relate to the response of this system? How does it behave? And more importantly, well, maybe not more importantly, but as a side note, we can examine how these eigenvalues are related to what are called the modes of the system and how we can excite specific modes in this system by choosing specific initial conditions. So with that framework in mind, let's talk about this. So this is nothing more than a state space representation of a set of linear ordinary differential equations, right? So the solution to this system, again, we discussed this in a separate video, is the solution of what the state vector does is basically given by the matrix exponential of e to the a t minus t0 times x of t0, right, plus the convolution integral of t0 to t of e to the a t minus tau times b u of tau d tau, right? So again, this portion over on the left, right, this was the autonomous response. Basically, it was the response of the system to initial conditions x at time t0, right? This portion over here is sort of the convolution integral part, or you can think of it as like a particular solution or the forced solution. Basically, this is the solution or the component of the state trajectory which is related to these inputs u of t, okay? So what I'd like to do now is, how about let's go ahead and consider the case where we are only looking at the autonomous response. I just want to see how the system responds by itself without any input. So in other words, I'd like to consider a simplified case where u of t is just 0 for all t, right? And to make our lives easier, let's just make t0 equal to 0. We'll start everything at time 0, okay? So in that case, this response of this system to no external inputs and only initial conditions is basically, we end up with what? We end up with x of t is equal to just the matrix exponential e to the at, right, times your initial condition, right? So this is how the system is going to respond. How this system is going to respond if you have no inputs, but your initial condition is non-zero. It's some value, right? Okay, so it's going to do this. So the question here is, as you can see, is it all hinges on this matrix exponential, right? So let's examine this, and to make the examination of this matrix exponential a little bit easier, let's think about performing a similarity transformation. So in our other videos, I think we have two videos on similarity transformation, one talking about just the mathematical idea of how to perform a similarity transformation on a general matrix, and then our second video was how to apply a similarity transformation excuse me, to this exact scenario of having a linear system defined by x dot is equal to ax plus bu and with an output equation, right? So if you haven't seen these other two previous videos on similarity transformations, please go ahead and do that first before proceeding. But I'll assume that you've seen that and you are familiar with the idea that we can basically consider a new set of states, right? So let's go ahead and consider let's call them alternative states. Let's call these alternative states z of t. Okay, and the way they're related to the original states is through a transformation matrix T, like such, okay? So in this case, we can basically perform our similarity transformation and we can rewrite we're going to perform the similarity transformation on this A by doing basically T inverse AT. This is going to get you a new matrix. Let's call this A tilde, right? And alternatively, the other way you can look at this is, let's go ahead and solve this for A, right? So basically just do the matrix inverses, right? And again, the idea with the similarity transformation is this T matrix is a square n by n full rank invertible matrix. So I should have no problem basically solving this to obtain A is equal to T A tilde T inverse, right? Okay, so if you plug that into the autonomous response, what do we end up with? We see that the response of the system is nothing more than e to the A. A is now can be rewritten like this, right? It's T A tilde T inverse times lowercase t, right? Times x0, right? Okay, so now let's take a closer look at this matrix exponential component right here, right? Maybe I'll put this in parentheses to identify what I'd like to look at, right? So again, this is sometimes referred to as the matrix exponential, right? Or sometimes it's the state transition matrix is another moniker that you may hear this, state transition matrix, okay? But anyway, let's take a closer look at that, okay? Let's go ahead and, boy, I ran out of space. Tell you what, give me a second to erase the board. Let's scoot this over and let's expand this term here. All right, so we're back. All we care about is this matrix exponential. So I've just written just that term, right? So it's e to this stuff, right? So again, we got to ask ourselves, what does that mean? And again, remember, e, the definition of e, right? It's just shorthand notation for this infinite sum, right? So we're going to sum from k equals 0 to infinity of basically whatever is to the e to the whatever. This thing, the whatever part, is just up here, right? So this is T A tilde T inverse times lowercase t. This thing is raised to the kth power all over k factorial, right? So that's again just the definition of E, right? It's just shorthand notation for this infinite series. Okay, we'll tell you what, let's write out a couple of terms of this so we can get a rough idea. So the k equals 0 term, right? That's pretty easy to see. It's something to the 0. Well, that turns out to just be an identity matrix over 0 factorial, which is 1. So the k equals 0 term is just the identity matrix, right? Okay, now let's get the k equals 1 term. So that is nothing more than T A tilde T inverse times lowercase t raised to the 1 power. I mean, here, I'll tell you what, let's just do it like this. 1 over 1 factorial, right? Okay, plus T A tilde T inverse times lowercase t to the 2 power all over 2 factorial, right? Let's just do one more term so we get the pattern, right? So I think everyone sees what's going on at this point, right? It's just over power 3 over 3 factorial plus da 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 da. It's for infinity, right? Okay, tell you what, let's expand this a little bit, okay? So this term is just identity. This is, now I can just write this as T A tilde T inverse times t, right? Plus, okay, this thing, let's write this out. Let's have, this is squared, so it's this thing squared. So I got to have T A tilde T inverse t, that's that thing, written, multiplied by itself, right? T A tilde T inverse t, like that. So that's the square term all over 2 factorial, right? Plus, again, let's just do this one more time so we all see the pattern. I gotta write this 3 times, which is a little bit of a pain in the neck, right? But this is going to pay off in a second. There we go. 3 times, that's cubed, all over 3 factorial plus higher order terms, right? Okay, now look at this. Okay, let's go down another line. Okay, so we end up with identity plus T A tilde T inverse times t plus, now let's look at this here. Okay, remember, big T A tilde big T inverse, these are all matrices, right? But little t, this is just a scalar, right? So that can move anywhere it wants, right? So I can move these lowercase scalar t's outside, okay? So we end up with what? T A tilde T inverse times A tilde T inverse times t squared. Does everyone agree that that's that top term? All over 2 factorial, right? I'll do the same trick over here, okay? So now we end up with t a tilde t inverse. I'm going to pull this t out, pull that t out, pull that t out. So we end up with this, a tilde t inverse, t a tilde t inverse, and then I got the t, lowercase t cubed. Over 3, all over 3 factorial plus yada, 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 right? Great. Now, if you stare at this thing, we see some nice things happening here. This becomes identity matrix, right? Because you got this t inverse t next to each other. Same thing here. This turns into an identity matrix. This turns into an identity matrix, right? And then look at this. This a is going to be right next to an a, right? So it's basically like a squared. And similarly here, you end up with an a. So it's like a cubed, right? So we end up with, well, sorry, not end up, but we're getting there. T a tilde t inverse t plus t a, a tilde squared t inverse times t squared, right? All over 2 factorial plus t a tilde cubed t inverse times lowercase t cubed all over 3 factorial plus yada, 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 right? Okay, great. Okay, now, here's one other interesting thing. Over here, identity matrix, would everyone agree that I could, if I wanted to, write this thing as t times t inverse? That's the exact same thing, right? And now, if you stare at this thing, you see that we have t's everywhere on the left of all these matrix expressions, and we have t inverses all on the right of all of these matrix expressions. And again, I don't have to care about this lowercase t. I can move this anywhere I want, right? So in other words, I can distribute a t off on the left and a t inverse on the right. I can pull that out of all of these terms. And again, that would happen no matter how many higher order terms I carried, okay? So what we can do is, let's come over here. This thing can basically be written as I'm going to pull off the t on the left, and I'm going to pull off the t inverse on the right, okay? So we end up with, I think this is going to be the identity matrix. So that's this thing, right? If I pull up the t on the left and the t inverse on the right, you're just left with an identity matrix. This is now just going to become what? A tilde t, right? Then we're going to get plus, that is going to be a tilde squared times t squared all over 2 factorial plus a tilde cubed times t cubed all over 3 factorial, right? That's that term after I distribute out the capital T matrices and the capital T inverse matrix, right? Plus, et cetera, et cetera, et cetera, higher order terms, right? So now, actually, let's do one last step, right? A squared times t squared, right? So again, I can just pull the squared out, and you can now write this whole thing as plus a tilde t plus a tilde lowercase t, this whole thing squared, right? That is just this term here, right? All over 2 factorial plus a tilde t cubed all over 3 factorial plus yada, 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 end parentheses, and then don't forget the t inverse on the outside, right? Now, if you look at everything inside this pair of parentheses, this should look really darn familiar, right? This is nothing more than e to the, oh shoot, I lost, sorry, this should have been a lowercase t. That's a lowercase t, sorry, lowercase t here, lowercase t there, right? Because that should have been, yep, that's the lowercase t right over here. Okay, sorry, now we got it. This whole thing in red, right, in parentheses, this is e to the a tilde t, right? This infinite series is nothing more than this, right? So at the end of the day, we end up with this whole thing. Maybe I better do this over here. This becomes the t times e to the a tilde t times t inverse, right? And what was this thing on the left? The thing we started with over here was this thing, right? So this is e to the t a tilde t inverse times t. Okay, box this up. Right? So we see this is the major result, is that with this matrix exponential under a similarity transformation, these t and the t inverses, even though they were part of the exponent to start with, they can sort of fall off on either side of the matrix exponential. So we can basically do the matrix exponential of this more simple term here first, e to the a tilde times t, and then we can do the the similarity transformation after we've computed this matrix exponential, right? That's the benefit of this entire thing, right? So we should ask ourselves, well, did we really save ourselves any work because we said, all right, we're interested in this matrix exponential over here, which, yes, I agree, this is a little bit more complicated, but we still ended up with a matrix exponential here, right? This e to the a tilde t is still a matrix exponential, right? Now, what makes this really interesting is what happens if you had chosen, let's go ahead and ask ourselves, what happens if you choose t, your transformation matrix for the similarity transformation, to be the eigenvectors of the original A matrix, right? So you remember in our video on similarity transformation, we saw that if you do this, what ends up happening is that if you start with a matrix, which could be, you know, fully populated, you perform the similarity transformation, right, using this very particular T, or transformation matrix, which is the eigenvectors of this, you end up with an A tilde, which is diagonal, right? And more importantly, what happens is that A tilde, not only is it diagonal, right, but it has the eigenvalues, lambda 1, lambda 2, all the way down to lambda n on the diagonals, and 0 everywhere else. Right? So under this modal, sometimes this is referred to as a modal transformation or a diagonalization process, right? Is you end up with an A tilde which is diagonal, okay? So now, under this, let's ask ourselves, what does this e to the A tilde t look like with a diagonal A tilde matrix? All right, so now let's look at that term e to the A tilde t, right? And again, we can easily see that e, this again is just shorthand notation for the infinite sum of the quantity A tilde t to the k over k factorial, okay? Now, we're going to recall that what we're looking for is what is if A tilde is diagonal, right? Like we just saw. I totally spelled that wrong. Diagonal. Right? Okay, so if that's the case, right, again, you can basically see that what's going to end up happening is that this scalar t can come out, and then what you're going to end up with is you're going to have, well, I'll tell you what, instead of me talking through it, let's write one more line of this. This can basically turn into A tilde to the k times t to the k all over k factorial, right? Now, earlier, the reason the matrix exponential was difficult was because you had to take matrix powers, right? But now, because A is diagonal, right? A tilde is diagonal, right? This thing looks just like, right, lambda 1, lambda 2, all the way down to lambda n and zeros elsewhere, right? So therefore, A tilde to the k, right, when you take the kth power of it, I mean, since it's diagonal, matrix multiplication or matrix powers is the same as just raising each element of the diagonal to the appropriate power. So this is just lambda 1 to the k, lambda 2 to the k, all the way to lambda n to the k, and zeros elsewhere, right? So what ends up happening is this entire term, right, can basically be written as, I can move this summation into the diagonals, right? So if you stare at this thing long enough, you'll basically end up with this is going to look like a matrix like summation from k equals 0 to infinity of lambda 1 times t to the k all over k factorial. That's going to be the 1, 1 element, and then the 2 element is going to again be summation k equals 0 to infinity of lambda 2 times t to the k all over k factorial. And this pattern is going to continue all the way down to summation k equals 0 to infinity of lambda n times t to the k all over k factorial. Right? And then it's going to be zeros everywhere else, right? So again, now if you stare at this and you look at any one of these diagonal entries, right, isn't this just shorthand for e to the lambda 1t? Right, or excuse me, this is shorthand for this summation, right? And similarly, this thing is just shorthand or is the expanded version of e to the lambda 2t, and etc., all the way down to the e to the lambda n times t, right? So what's awesome about this is that in the case where a tilde is diagonal, this matrix exponential actually comes out to look something like e to the a tilde is actually just a diagonal matrix of e to the lambda 1t, e to the lambda 2t, all the way down to e to the lambda nt with zeros everywhere else. So it's basically, again, diagonal. Okay? Now, the reason this is important, right, is let's go back. Why did we examine this e to the a tilde t? Okay? So if you remember, in our earlier discussion, the whole reason we started down this path is we said that the response of the linear system, right, the autonomous response of this linear system when there was no input, right, was this thing came out to be t times e to the a tilde t times t inverse times the initial condition, right? That's why we did all that work to basically get to here. And now we understand what this matrix exponential looks like. It is just this matrix, right? So again, let's write this out to be completely explicit, okay? So this is the transformation t. Then this matrix exponential is just this thing here, right? It's e to the lambda 1t, e to the lambda 2t, all the way down to e to the lambda nt with zeros everywhere else, right? This times the matrix t inverse, and then this initial condition is basically just a vector of x1 at time 0, x2 at time 0, all the way down to xn at time 0. Okay? And this is now the autonomous response of the system, right? The natural, unforced response of the system. And this is an extremely powerful formulation, because if you stare at this long enough, what do we see? We see that again, this is going to be a trace, right? This is some trajectory, right? Because it's a function of time, right? The only place that time shows up in here is in this state transition matrix, this modal state transition matrix, right? Or this diagonal state transition matrix. And in fact, what we see here is that the only place you see the t terms is they're all e to the lambda 1t, e to the lambda 2t, all the way up to e to the lambda nt. So we see here that basically these lambdas, right? You remember these lambda i's were the eigenvalues of the original A matrix, right? So these are basically telling us, the eigenvalues tell you the response of the system. The actual trajectory of the system, you can see it cleanly here, it's just a linear combination of all of these e to the lambda 1t, e to the lambda 2t's, e to the lambda nt terms, right? So this is why we care so much about where the eigenvalues of the A matrix are, is because that is going to dictate the complete autonomous response of the system, right? That's the only way that you get any time varying behavior is from these e to the lambda t terms, right? Again, this transformation matrix t, it's just going to linearly combine them. Same thing with this t inverse, and all of these initial conditions are just constants, right? So this, again, I think is pretty much the key to understanding why we care about where the eigenvalues of the A matrix are, and we care because they make up, these are sometimes referred to as the modes of your linear system. So this might be considered like your mode 1 or your first mode. So this is like maybe mode number 1, and then this is sometimes mode number 2, all the way down to say mode n, right? And you can see why they're called these principal modes is because they're almost like basis functions, right? Which are then used in a linear combination fashion, right? According to this equation, to get the entire response of the system, right? So again, I'm kind of belaboring the point and talking more about it than probably we really need to, because it is so important, because this is, it lays it completely bare, right? There's no mystery any longer about what the system behaves like, right? So if these lambdas, if they are, you know, very far in the left half plane, all of these terms are going to decay very quickly, and you're going to have a very stable system. Conversely, if just one of these terms, right, if these lambdas, if only one of them has a positive real part, that means somewhere in here there's going to be an e to the positive some number t, which is an exploding exponential. And then by the time you work it through with these t inverse and initial conditions, you can see that one or more of your states here are likely going to be exploding to infinity, right? And again, this is a very quick off-the-cuff discussion on how the location of the eigenvalues govern the response of the system. If you want a more in-depth discussion of that and a more close analysis about how the pole locations map over to performance characteristics, right, check out some of our other videos where we discuss that pretty extensively, right? So, okay. With that being said, I think we've got most of the first part of this discussion down. We now understand what all the modes of the system are, right? The modes of your linear system, right, are basically the principal underlying basis function behaviors of how the trajectory of the state trajectory of this linear system is going to behave under a non-zero initial condition, right? It's going to be a linear combination of all of these modes, right? So what's interesting now is the next thing we should maybe do is let's talk about how can you maybe try to excite one or more of these modes by themselves. All right, so now let's talk about how can we excite a specific mode. And when I say excite that mode, I mean, can we use an initial condition so that the output state trajectory only has a specified mode showing up in the response? So to set the stage for this, or to make it a little bit easier, maybe instead of looking at the original system, let's go ahead and look at the transformed system. And again, if you need a refresher on how to do this, check out our video on similarity transformations. But I'd like to now look at the transform system of z dot of t is equal to a tilde z of t, right? Where a tilde is our transform system underneath the similarity transformation, right? So again, you can think of this as basically the exact, a very similar system to the original one. It just has a different set of states, right? But the eigenvalues and other behaviors should be similar, okay? Now, this, right, we know that the response of this system, it's just some other linear system, right? So we know the response of this thing is going to look like z of t is going to basically be e to the a tilde t times the initial condition in the transformed state vector, right? Now, again, let's go ahead and use our a tilde, which is diagonal. Right, so we're going to diagonalize the system or do a modal similarity transformation. Okay, so if that's the case, right, we again saw last time that this matrix exponential, it's really simple. It's actually just e to the lambda 1t, e to the lambda 2t, all the way down to e to the lambda nt, and zeros everywhere else. And then again, your initial condition for z, it's just going to be z1 at time 0, z2 at time 0, all the way up to zn at time 0, right? Okay, so now, again, we can now do this matrix multiplication pretty easily, right? This is just a diagonal matrix times a scalar. So we're going to end up with the trajectory in the transformed set of states is going to look nothing more than e to the lambda 1t times z1 at time 0, e to the lambda 2t times z2 at time 0, all the way down to e to the lambda nt times the nth initial condition at time 0. Right? Now, this is really interesting because now if you look at this, the actual response of the system, sorry, that should have a bar, right? It's really, you can see this pretty cleanly. It's just the first mode shows up as the first state, the second mode is the second state, etc., right? So now, if you go ahead and choose a very specific initial condition, you can basically knock out every other mode and just keep the one you want. So in other words, what I mean is, let's go ahead and choose, how about as an initial condition of basically all zeros, but you put a 1, put this here at, say, the ith position or something, right? So it's all zeros, and you just put a 0 in the, or so a 1 in the ith position. What that's going to do is, you're going to see here is, since all these z's except for zi are 0, what you're going to end up with is, if you excite the system with this specific initial condition, what you end up with is basically z of t is going to look like, again, it's going to look like a whole bunch of zeros, but then it's going to pick up this mode of e to the lambda I t times z. Or I guess zi, I said, we said was 0, right? So it's going to be 0, 0, right? Okay, so here, in this case, what we've done is we have just excited only the mode of e to the lambda I t, right? So by choosing an initial condition in the transform set of states with a 1 in the ith position, you basically make it so that the state trajectory, the only term in here is basically that mode, right? So that's pretty darn cool. The only thing that we probably want to think about, though, is we really care about this initial condition x0, right? I really don't so much care about z. Whoops. See if I can draw a z here. I don't really care about z0, right? I really care about x0 because I really want to excite this original system and see if I can get the response to have only a specific mode, right? Well, lucky for us, that's actually pretty easy to do, is we just need to basically transform the initial condition from z0 to x0, right? And we can easily do that using our similarity transformation definition, right? So it's just the transformation matrix T times Z0, right? And again, remember, in our case, to diagonalize this T here was basically the eigenvectors of A, the original A matrix, right? Okay, so this, theoretically, if you use this initial condition on this original linear system, we should excite it in the sense that the state trajectory in X now will only have terms looking like e to the lambda it. So we'll only exhibit behavior from one mode, okay? So tell you what, give me a second to erase the board and let's go over a numerical example of this. All right, so let's consider this numerical A matrix for our example. So if you go ahead and take the eigenvalues and eigenvectors of this, you get eigenvalues down here of lambda 1 of -2, and then lambda 2 and 3 are complex conjugate pairs, like such. And then the eigenvector matrix in column form is like this. So here's the first eigenvector associated with this first eigenvalue. Here's the second eigenvector associated with the second eigenvalue. And similarly, here's a third eigenvector associated with this third eigenvalue. So what we may want to do now is, again, use our diagonalization technique and use this eigenvector matrix as our transformation matrix T, okay? So if we do that, what we can do is now think about trying to excite, let's start with this first mode. Let's try to excite only this mode, okay? So we saw earlier that all I need to do is to basically choose an initial condition vector in the transform space, or transform state vector, like this, 1 in the entry associated with this first mode. And if you do that, this ends up working in the sense that what we can do is go ahead and transform this into the equivalent initial condition using our transformation matrix, right? So if you do this, you end up with an initial condition of, didn't I write this down here somewhere? Yes, I did, okay, of 1, 0, 1, okay? So here's your initial condition that if you apply this initial condition to this original linear system, what we should see is we should see the trajectory of the state vector x, right, only have a mode associated with this first eigenvalue, right? So if you do that, if you go ahead and compute the matrix, the state transition matrix, and compute the trajectory, right, you come up with, this is basically e to the at times x0, right? So just do this operation, right? And indeed, what you end up with is, at the end of the day, I'll leave this as an exercise to you to do this in Mathematica or whatnot, but you'll end up with e to the negative 2t 0 and e to the negative 2t. So yeah, this totally checked out, right? If you look at this state trajectory, which is excited by this specific initial condition, only has this mode associated with it, or with this here, right? So we only see the first mode showing up in the response. So there's no oscillation, there's just this pure decaying exponential. So this is interesting that in this sense, even though the system was unstable, right? You saw that these other eigenvalues have positive real parts. So under normal situations, the state trajectory is going to blow up. But if you use this very specific initial condition, actually, it looks like the state trajectory decays. So that's actually kind of interesting. Okay. Now, how about the second mode? Let's go ahead and move our attention now to this second mode, and this is where it gets a little bit more interesting. Okay. So now let's try to excite this mode. Right? So if we do that, let's go ahead and choose a Z0. Let's naively choose, how about 0, 1, 0? Okay? Because again, we're going to try to excite the mode that is associated with the second eigenvalue. Okay, so again, let's go ahead and do this. X of 0 is t Z0. Right? So you go ahead and do that, and you end up with, what's interesting is you'll end up with an initial condition which is actually imaginary. So you get this thing here, for the interest of completeness, let me go ahead and write it down. I did this in Mathematica. It came up with negative 9i plus 5 root 3 all over 3i plus 7 root 3. That's the first element. The second element looked very similar. 3 times the quantity, negative 7i plus root 3. That quantity all over 3i plus 7 times root 3, and then a 1. So you get this imaginary initial condition, which if you do plug it into this, okay, what you do end up with our state trajectory is, yes, it does indeed look like the response looks like 0 and then e to the 3 halves plus, let me make sure I got this right. Yeah, plus root 3 over 2t and 0. Okay. So, sorry, I think this should be like that. Should there be an I here? I think there should be an I here. Did I get that right? Yep, there we go. Okay, so yes, again, the state trajectory in this particular case, right, does only have this second mode, but this is imaginary, right? You can't use a exponential to trig identity to try to insert cosine and sines, and hopefully you can try to get all the imaginary terms to cancel, but they're just not going to in this case. And you can kind of see that this is also, this initial condition of an imaginary initial condition really doesn't make a ton of sense in this situation. So the situations where you have complex conjugate pairs, as you most likely know, is they always come in pairs. You usually want to excite them in pairs, because these, when you have the complex conjugate, if you keep them together as a pair, that's when you can actually simplify using cosine and sine. So what we should do is, let's actually excite both of these modes at the same time in equal proportion. So what that means is we need to come back up here and let's turn this into a 1 here. Okay, so if you do that, this initial condition actually becomes much more reasonable. right? If you do that, you end up with 1, 0, 2, okay? And now, if you go ahead and use this initial condition with this state transition matrix, actually, this guy also becomes a lot more reasonable, and the state trajectory, if you go ahead and fully simplify it, again, I'm going to leave this as an exercise to the reader if you've got Mathematica or something like that, but this can be rewritten as e to the 3/2 t times the quantity cosine root 3 over 2 t plus root 3 sine of root 3 over 2t. I think I'm missing a parentheses. Yeah, there's that parentheses. And then this entry is 2 root 3 e to the 3/2 t sine of root 3 over 2t. And then finally, the third entry is 2 e to the 3/2 t cosine of root 3 over 2t. Great, so here we go. Here is your state trajectory, and again, what's interesting here is you only see the response due to the second and third modes, right? There is nothing in here which has anything to do with e to the negative 2t, right? Because this is the first mode, and we did not excite that here, so in this sense, the response that you get to this particular initial condition looks like this, right? With only the second and third mode showing up, right? Now, again, what's just to be complete about this is we have to actually excite both of these modes in the same proportion. If you, for example, change this from a 1 to a 2, right? Here you might say, okay, yes, I'm still exciting both modes, but I'm not doing them in equal proportion in this transform state space, state vector space. This is going to yield an initial condition which is actually back to imaginary, right? This will turn into a, what did I end up with? 1/2 times 3 plus root 3i, and then root 3i, and then 3. And then this thing, again, if you plug it in, this is now also going to change. It's going to become imaginary with i's all over the place. In the interest of time, I'm not going to write it out, but take my word for it. So again, this is a little bit interesting, right? So at least though, at the end of the day, now we have a technique, right, that is going to allow us to excite a particular mode and see that response show up in the state trajectory trace, and that mode alone, right? Okay, let's see. Give me a second to get a little bit more space, and I want to talk about one more little small item. All right, so I've cleared off half of the board, and the last thing I want to talk about is how we can look at the eigenvectors as sort of these quote-unquote, I'll call them participation factors. And the reason I'm going to call it this is because if you look and recall our similarity transformation, right? X of t was t times z of t, right? Okay, and remember our t matrix was this thing down here, which was just basically a matrix of the eigenvectors in column format, right? So again, this was the first eigenvector associated with this first mode. This was the second eigenvector associated with this eigenvalue, which, you know, is a mode, etc., right? So why don't we just substitute that in, right? So this T matrix, right, it's nothing more than V1, V2, and V3, right? Okay, and then we said that the solution to our transform system, right, the state trajectory z of t, right, of this system, right, that was given by what? It was given by our matrix exponential e to the, whoopsies, a tilde of t times z naught. All right, and then going one step further, remember that the idea with the A tilde matrix, right, was it was modal, it was diagonal, right? So this matrix exponential turned out to be really simple, right? It was e to the lambda 1t, e to the lambda 2t, e to the lambda 3t, and then zeros everywhere else, right? Okay, this times, and then our initial condition in z, that was just z1 at time 0, z2 at time 0, and then z3 at time 0, right? Okay, so now you multiply this whole thing out and you see what we end up with is something that looks a little bit like this, right? You have v1, the vector, right, times z1 at time 0 times e to the lambda 1t plus v times z times 0 e to the lambda 2t plus v3 times z3 at time 0 times e to the lambda 3t, right? So this was the state trajectory, right? The original state trajectory x, right? And you see, just like we saw earlier, it's made up of a linear combination of the modes, right? So again, we see, you know, here's the first mode, this e to the lambda 1t, second mode e to the lambda 2t, and then the third mode e to the lambda 3t. And now, what we have in front here is this z10, z20, z30, those are just scalars, right? And these vectors now, effectively, they're sort of telling you how much of this mode shows up in the response of x of t, right? So, for example, if you look at v1, right, let's look at v1. This is v1. I'll just kind of do this in a dashed line, right? This is v1, right? That's the first eigenvector, right? So if you look at this equation, you see that, okay, this mode of e to the lambda 1t, and you remember, this was the stable mode, right? This was that exponentially decaying e to the negative 2t, right? This nice, happy, stable decaying behavior, it basically only affects state 1 and state 3, right? Because there's a big fat 0 here in the number 2 position. You'll see that you'll never have an x2 of t, which is some function of e to the lambda 1t, right? This is not going to happen because this v1 is basically telling you that how much this mode participates in the response x of t is basically a lot, nothing, a lot. Right? So you can think of these eigenvectors as basically telling you, this is why I'm kind of dubbing them as, you know, quote unquote participation factors. You can see how much does each mode appear in the state trajectory x of t by examining the eigenvectors, right? So what you see in this case that, yeah, this mode, this stable e to the lambda 1t shows up in states 1 and 3. That's how it manifests itself. And then the modes number 2 and 3, the sinusoidal, right? These exponentially increasing sinusoidals, right? These unstable oscillations, they are going to show up in all 3 states, and you can see that because these 3 eigenvectors, these 3 elements of each of their eigenvectors are non-zero, right? So they show up in all of their trajectories, right? So the way you could think about that is, you know, for example, let's excite this original system with some, you know, some arbitrary initial condition, you know. So for example, this x0, let's just choose for giggles, I don't know, 1, negative 2, 3, okay? So again, this is x at time 0, right? We're gonna perturb the original system using some kind of non-zero initial condition, and we saw that since we didn't pick this intelligently or carefully, we expect to excite or show all of the modes in the response x of t here, right? And in fact, if you do that, and you solve for, you know, what does x of t look like, right, using our e to the at times x0, right? So you do the full matrix exponential however you'd like to do it and get this trajectory. In fact, let me do this. I will do this myself in mathematics, and I'm going to show you a screenshot of it. And as you can see here, what ends up happening is examine that expression very closely. Look at the expression for x1 of t, right? That's the top row. I guess that's the first element of that vector, right? Notice that term, you'll find an e to the negative 2t there, right? And you'll also find these increasing oscillations, these increasing sinusoidal oscillations show up in x1. But now, go one row down, right? Now look at the second element of that response, the response of x2 of t. Notice there is absolutely 0 terms that say e to the negative 2t, right? That does not manifest itself because the participation factor associated with this first mode and its influence on the second state is 0, right? So you don't see it, but you see the oscillatory effects because of these two entries here. Right? And then similarly, lastly, we can do the same analysis for the bottom row or the bottom entry of the the third element, which is the x3 of t response. And again, you see that e to the negative 2t show up because, again, that participation factor is non-zero, and you see the oscillations show up as well because, again, those participation factors are non-zero. So this is kind of interesting. It allows us to map a little bit how these different modes can manifest or present themselves in the actual state trajectory. You can have a little bit of an idea of which modes are going to affect which states. And again, we're going to take a little bit closer look at this when we start talking about some lateral, directional, and longitudinal models of aircraft. That's one example of where this type of an application might show up. And again, we'll look at that in a future video. So with that being said, I think we've come to the conclusion of this discussion here, where we talked a little bit about these eigenvalues and how they map to what we're referring to as modes of a linear system. So again, the eigenvalues we clearly see are just the eigenvalues of the A matrix, and then the modes that you might associate with this, or what people kind of refer to as modes, are these terms that look like e to the lambda it, right? Basically, they tell you how does the system behave, what are the base functions, what are the base behaviors of this system, right? So, like I said, I think this is probably a great spot to leave it. I hope you enjoyed the video, and if so, I also hope you'll consider subscribing to the channel. If you just scroll a little ways down and click on that subscribe button, it really does help me continue making these videos. We've got a lot more videos on linear system theory, control theory, flight mechanics, things like that, and the new videos come out every single Monday, so I hope you'll join us at one of these future discussions, and we can all learn something new together. So, until then, I think I'll sign off. Talk to you later. Bye.